Okay, did you get the same thing I did? When we look at this, this is the anode, this is the cathode, so we know the anode is losing electrons. So at the anode half, aluminum solid is making aluminum 3 plus 3 electrons. And the cathode reaction is the reduction of the copper 2 ion, so it's gaining 2 electrons to make copper solid. We need the same number of electrons in each half reaction, and I have 3 in the aluminum half and 2 in the copper half, so I have to multiply by the appropriate coefficients to get the same number of electrons in each half. And when I do that, I get 6 electrons, I combine the 2 halves, and then my 6 electrons cancel, and what I'm left with is 2 aluminum solid and 3 copper 2 plus yields 2 aluminum 3 plus 3 copper solid. So this is kind of going backwards from what we did when we were reviewing balancing the redox equations. Now, why are we interested in these things as chemists? Because galvanic cells are very useful to us because they push electrons through an external circuit and they provide energy or electricity for us, or battery power, whatever you want to think of it. So how do we do this? Well, you know that you've had batteries all your lives, right? And you look at them and it might be a 9-volt battery, or you can look at the certain voltage on there. And you know that the voltage listed on your battery is what it's supposed to have when it's new. And then as its life goes on, the voltage drops because it gets used up. Some batteries can be recharged, some cannot. They get recycled, right? So we can calculate information about the chemistry by using the cell potential. And the cell potential, we call it E sub cell. It is the maximum potential that a given cell is capable of generating. So when you talk about that 9-volt battery that you buy for your smoke detector, 9 volts is the most it's going to have. At some point, 6 months later, it may not be providing 9 volts anymore. So we talk about standard conditions for cell potentials, and we use the little superscript 0. When we do this, it means that the concentrations of all the ions in our cells are 1 molar. The temperature is 25 degrees Celsius, or 298.15 Kelvin. And if we have any gases there, the pressure is 1 atmosphere. So those are standard conditions. And there may be a time when your only clue about what this information is the fact that that little 0 is written there. So you may need later on to say, okay, that's a 1 molar concentration of my electrolytes. And we measure the cell potential in volts, or electromotive force is measured in volts, and we define a volt as 1 joule of energy per coulomb of charge. Now, we introduced the Faraday constant briefly when we did our last lab activity. We'll go over that again. So when you look at this tabulated data, you'll see that this says standard reduction potentials. So everything in this chart is written as a reduction. And we have randomly decided that the hydrogen electrode is the standard, and we compare everything to hydrogen. So about halfway down this list, you'll see the hydrogen electrode, and it has a standard cell potential of 0 volts. So we compare everything to hydrogen. And when you look at some of these things, the things at the top have a positive voltage for the reduction. Things that are lower than hydrogen on the list have a negative voltage for reduction. And you may remember from Chem 111 when we talked about single replacement, we said we were using the activity series. So the activity series is related to the cell potentials. So this is a chart that you're going to need to have in your hands when you're doing problems. You do not memorize this. It is provided to you in the note packet, so when you're doing homework, it's there, readily available. It will be provided to you on the test if you need that information. So how do we deal with this? We arrange cells in a series to make a battery, to generate energy. And that battery will have a cell potential that's equal to the sum of the potentials for all the cells. We don't just put one cell together to make a battery. If you took a knife and cut your batteries in half, and I do not recommend that you do this, okay? Don't go home and do this just to look at it. But if you were to do that, you would see that there's a series of little cells all stacked up on top of each other in the battery. If you ever are jump starting your car and you're not paying attention and you blow up your car battery, after you get out of the way, of course, and take a shower because it sprayed sulfuric acid all over you, because that's one of the half cells in a car battery, then go back and look at the blown up battery and you can see the individual cells in there. Or if you ever do that, save the blown up battery and bring it to me, and then I can show my future students and tell them not to do that. You have to be really careful of that so you don't get injured or burned really badly. So the reduction potential tells us numerically how well something can get reduced. So if it has a higher reduction potential, it will be the thing that can gain the electrons. When you look at two cells, they will each have a reduction potential, and when we connect them with a wire, then the one with the bigger reduction potential is the one that will kind of win, and it will get reduced, and the other half cell will have to undergo oxidation in the process. So when we hook these cells up together, we can predict what's going to happen spontaneously. Because what will happen spontaneously is the one with the bigger reduction potential will get reduced. The one with the smaller reduction potential will get oxidized. So let's go ahead and look at an example. For any two cells, the standard cell potential is equal to the standard potential of the reduction half for the cathode minus the standard potential for the oxidation half, which is taking its place at the anode. This will be the bigger number. This will be the smaller of the two numbers. Now remember, when we talk big and small, we're talking about the more positive number. So you could have a positive number for one and a negative number for the other. And in that case, the negative would be the smaller number, even if the magnitude of the negative number is bigger than the magnitude of the positive number. It's the more positive number. So let's look at an example, and I think it'll make more sense. We have the silver-copper half cell. Two silver ions are reacting with copper solid to make two silver solid and copper 2+. So we can look at this and write out the two half reactions. Two silver will need 2 electrons to turn that into 2 silver solid, because we had silver ions on the left. And we have copper solid becoming copper 2+ plus 2 electrons. So when we look at this, we say, well, what is getting reduced and what's getting oxidized? What's getting reduced is gaining electrons, so the silver ion is getting reduced, and the copper solid is getting oxidized. So we grab our chart and we go look up the standard cell potentials. The standard cell potential for the silver ion is a positive 0.80 volts. And the standard potential for the copper is equal to a positive 0.34 volts. So we calculate the standard cell potential. E0 for the cell is equal to E0 for the reduction half, the silver half, minus E0 for the oxidation half, the copper. So that's equal to 0.80 volts minus a positive 0.34 volts. So we get 0.46 volts is the standard cell potential.
And you don't switch the sign on the copper because it's...
You don't switch the sign because you're doing that by subtracting. Okay? I'm subtracting the copper half. So I'm taking the number out of the chart and I am subtracting it. We always think of it as the reduction half minus the oxidation half. So you don't change the sign and then subtract it, because then you'd be doing that double.
What I mean is in the chart it's Cu2 plus 2E minus. Instead of Cu gives us Cu2 plus 2E minus.
I am turning it around because, okay, so here's the reaction we're discussing. This is written as a reduction because everything in the chart is a reduction. But in my chemistry, it is getting oxidized, so it's going backwards.
But the number's the same, was my question.
You use the reduction potential and you subtract it, so I'm changing the sign by subtracting it. Okay, you don't change the sign and then subtract it.
Right.
Okay? So it's the reduction minus the oxidation half. So you don't change the sign, you just subtract it. And you also do not multiply it. Remember in the enthalpy, free energy, and entropy charts, if we had a 2 in the balanced equation, we multiplied the number in the chart by 2. You don't do that here. You just take the reduction potential minus the oxidation potential.